The standard model of neuroscience treats memory as a collection of discrete, localized records. In this view, learning is the process of adjusting individual synaptic weights, storing isolated electrical signals, much like data on a hard drive. The Brain Kinematics Model offers a different physical substrate. Here, the brain operates as a history-dependent viscoelastic continuum. The network acts as a single topological mesh, constantly vibrating and deforming under physical tension. Information is not stored in isolated pockets. Instead, memory is progressively incorporated directly into the physical architecture of this continuum. The brain cycles through stress, structural strain, redistribution, and eventual stabilization. Memory, then, is a process of structural deformation. What begins as a temporary mechanical strain eventually harden into permanent biological architecture. Every novel experience you encounter generates a distributed strain field across this neural continuum. Initially, this field is highly dynamic and completely reversible. Repeated activation, whether through waking rehearsal or emotional reinforcement, leaves a stable residual curvature in the mesh after the initial stress relaxes. We call this structural signature a strain mark. The duration of any memory is strictly proportional to the structural stability of its underlying strain mark. A light, transient deformation fades rapidly, while a deep, stabilized curvature persists. When you forget a recent event, or a new memory is easily modified, the brain is not failing. The neural continuum is simply behaving exactly as an elastic material should before permanent structural stabilization occurs. Maintaining both high stability for old memories and high plasticity for new learning creates a physical contradiction. The continuum cannot be rigidly permanent and highly elastic in the exact same location. We can observe this constraint in metallurgy through work hardening. If you continuously bend a piece of metal, the material at the stress point becomes increasingly rigid and brittle until it resists new deformation entirely and will eventually snap. If the brain allowed every single sensory experience to instantly form a deep, unyielding strain mark, the neural continuum would experience catastrophic work hardening. The capacity to learn anything new would halt. Forgetting is the mechanical price paid to avoid this rigidity. The continual redeformation and erasure of immature strain marks preserves localized zones of high elasticity, keeping the continuum adaptable. Optimal brain function relies on a dynamic equilibrium. Deeply rigid, stabilized strain marks hold your accumulated knowledge, while flat, elastic zones remain ready to capture novel data. As you accumulate experiences, you do not simply dig isolated, deeper holes in the mesh. Large strain marks progressively branch outward into finer, highly localized topological configurations. This creates a semi-fractal organization. Physical, nested curvatures map directly to hierarchical conceptual relationships. Broad structures like living organism branch into mammal, down to dog, and finally out to the specific memory of your childhood dog. Plasticity varies across this fractal network. Broad foundational concepts at the root are mechanically locked. You cannot easily unlearn the concept of an animal. The terminal sensory branches at the edges remain highly plastic, ready to be overwritten by new details. This semi-fractal geometry is the biomechanical substrate of mental abstraction. Culture, scientific theories, and your personal worldview emerge directly from these nested physical deformations. Conceptual reasoning is not a separate cognitive faculty operating above your memory. It is the geometric outcome of the continuum integrating vast amounts of sensory strain over time. The maturity of a memory cannot be measured solely by the chronological age of the event. Time alone does not dictate stability. This scatterplot charts the life cycle of a memory across two simultaneous axes. As a strain mark matures, it must gain structural stability on the x-axis, while also increasing its relational complexity on the y-axis. Repeated reconsolidation actively strips away unstable episodic details, like the exact lighting or sounds of a specific day. The brain discards these sensory variables to extract invariant organizational principles, moving the memory up both axes as it connects to a wider conceptual web. Memory consolidation requires creativity. It sacrifices chronological precision to construct the heavily integrated, abstract semi-fractal architecture that forms your personal identity. We can observe this architecture directly during sleep. With external sensory input shut off, residual neural strain flows preferentially along the existing paths of least resistance within the semi-fractal network. Consider a common dream narrative. You are panicking because there is no seat for you in a classroom. Suddenly, you are sitting in the lecturer's chair, but you know you don't belong there, leading you to emotionally withdraw from the room entirely. Traditional analysis asks why the symbolic story changed. The kinematic approach asks what this jump reveals about the organization of your physical memory network. Abrupt dream transitions represent consolidation boundaries. The strain flow hits a gap and leaps between memory hierarchies that differ drastically in physical age and their level of abstraction. The bizarre, nonlinear logic of dreams provides a highly precise diagnostic readout. It traces the geological fault lines within your evolving memory continuum. To quantify these leaps, the Brain Kinematics Model utilizes the memory consolidation gradient. This metric measures the gap across 3 dimensions: the temporal distance between memories, the hierarchical distance across the network, and the abstraction distance, moving from a concrete episode to a generalized symbol. A small gradient transition might simply move between 2 highly plastic recent sensory memories. A massive gradient jump occurs when a minor daily stressor instantly triggers a deeply locked lifelong theme regarding your identity. A single dream does not have one chronological age. Every dream is a consolidation spectrum, a real-time traversal across the varying maturities of your brain's structural architecture. Learning is the progressive stabilization and hierarchical integration of strain marks. Forgetting is the mechanism that safeguards adaptive plasticity. This physical mechanism scales perfectly. The rules governing a localized dent on a microscopic mesh also generate the highest levels of conceptual thought and personality. Memory is not a chronological, active, viscoelastic topography that you continuously build, deform, and physically inhabit.